Okay, we should be good to go. So just for the purpose of the recording, to catch up, we started off with the shift formulas. We drew the point Q prime, which is on the opposite side of P. The angle is pi plus theta. And if we relate the coordinates of Q with those of P, then following the computation that we have here, we get that cosine pi plus theta is minus cosine theta. Sine pi plus theta is minus sine theta. Last, the formula for the tangent follows quite nicely from the previous two formulas. You just write the tangent as sine divided by cosine. And you use the previous two formulas, so that's minus sine theta minus cosine theta. And that gives you the minus cancels, so that's tan theta. Then the next set of formulas up are shift formulas, where now the shift is not by pi, so you don't add pi to the angle, but you add pi over 2 in each case. And now you see something interesting happen. So if you add pi over 2, sine turns into cosine, cosine turns into minus sine, and also tangent function turns into minus cotangent. So if you sort of think of sine and cosine being related, sine turns into cosine, cosine turns into minus sine, and tan and cotan are also related. So tan turns into cotan, and it turns out cotangent will turn into tangent if you add pi over 2 to the argument. So here we will not give the proof. So proof not given, but these are very useful formulas to know and to understand. There's a similar looking set of formulas that again involve pi over 2 and pi over 2. But now instead of adding pi over 2 to the angle, what we do is we subtract the angle from pi over 2. So we have pi over 2 minus theta. And the reason why I highlight these formulas in particular is because if you look at the right-hand side, you again see this phenomenon where sine turns into cosine and cosine turns back into sine. But the signs plus or minus, and sine, it's a lot of signs, but the plus or minus signs, you see they work out nicely. So sine turns into plus cosine, cosine turns into plus sine, and you don't have to remember, is it plus, is it minus, and so on. Here, as far as proofs go, where do these formulas come from? We can actually show or derive these formulas quite easily. So for instance, for the first one, if we take sine pi over 2 minus theta, then that is in fact the same as writing pi over 2 plus minus theta. And now I use the formula from the previous slide to say sine pi over 2 plus an angle, that's cosine of that angle. So here I can say this is cosine of whatever I add to pi over 2, so cosine of this minus theta. And now cosine of minus theta, that is cosine theta because of the even / odd formulas. And you can do the other formulas yourself, deriving the cosine formula and the tan formula. So I'll leave that as a challenge for you. Let's have a look at a quick example of what we can do with all these formulas, or actually, let me skip this example just in the interest of time and go directly to the addition subtraction formulas, and then we'll do a slightly larger example near the end. So the addition subtraction formulas, these are really the workhorses, so to speak, workhorse of trigonometry. And what do I mean by that? Well, using these formulas, you can derive basically everything else. And there's in total 4 addition subtraction formulas. Again, we will not cover the proof. I just want to point out the general structure. So what they do is they take the sine or the cosine of the sum of 2 angles, alpha plus beta, or the difference of 2 angles, and they turn it into a sum of a sine times a cosine and a cosine times a sine, or a cosine times a cosine and a sine times a sine, depending on whether or not you started with a cosine or a sine. So I would say I'm never a big fan of memorizing things. These are probably formulas that you should definitely have on your formula sheet, and you should be able to recognize them and apply them without having to think too much about it. So I think what you'll find is, if you do plenty of exercises, that you'll memorize these formulas pretty much as a given. So what does the structure of the formula look like? So let's start with the sine formulas. So if you have sine of a sum, alpha plus beta, or a difference, alpha minus beta, then what you have on the right-hand side is always sine, cosine, cosine, sine. And here you see the same structure. So sine, cosine, cosine, sine. And the only difference is in the plus or minus in between the 2 terms. So if you do sine alpha plus beta, then you get a plus here. And if you do sine alpha minus beta, then you get a minus here. And now for cosine, what happens? Well, similar looking structure, just a bit different. So cosine will always give you something, cosine alpha plus beta or cosine alpha minus beta will always give you something cosine, cosine, and then sine, sine. So here too, you see cosine and then cosine, cosine, sine, sine. And now, what does the plus and the minus work out to? Well, here you have to be a bit careful. Cosine alpha plus beta gives you cosine alpha, cosine beta minus sine alpha, sine beta. And cosine alpha minus beta gives you cosine alpha, cosine beta plus sine alpha, sine beta. So that's just how it is. You have to be a bit careful when you deal with the cosine to get the signs in the right place. But that's how it is. So let's maybe have a look at an example. So let's compute the sine of 7 pi over 12 as an example of the addition and subtraction formulas. And at first you say, well, what does that have to do with addition or subtraction? Or even more to the point, hey, you have something 7 pi over 12. I don't know how to make sense of that. But if you think about 7 over 12 for a little bit, 7 pi over 12, then maybe one of the things that you'll see is that this is actually 3 pi over 12 plus 4 pi over 12. And if I simplify that a little bit, that's pi over 4 plus pi over 3. So that thing that I want to calculate, I can write as pi over 3 plus pi over 4, the sine of that. And this is a good observation to make, because what you have here, these two pi and pi over 3 and pi over 4, these are known angles. I know what the sine and the cosine of that is. So now I can apply my addition subtraction formula, and I get sine pi over 3 cosine pi over 4 plus cosine pi over 3 sine pi over 4. Just straightforward applying the addition formula for sine. And now I can work out what each of these terms are. So sine pi over 3, that is square root of 3 over 2. Cosine pi over 4, that's square root of 2 over 2. And then cosine pi over 3, that's 1/2. And sine pi over 4, that's another square root of 2 divided by 2. And now I have basically the answer. Let me just clean it up a little bit. I can factor out a square root of 2. I get a square root of 3 plus 1 divided by 4. So in general, this last step, just cleaning up the numbers, it's good practice. If you don't do this on the exam, if you leave things like this, then maybe we'll subtract 1 point out of 10 for not making it a bit cleaner, but that's fine. And then the last set of addition subtraction formulas that we will cover in this class, they involve the tangent function. And at first sight, they look a little bit complicated. So if you have tan of alpha plus beta, what you get on the right-hand side here involves a lot of tan alpha and tan beta, but you get a fraction. So at first sight, this looks a bit complicated. But if you play with this for a while, you'll see that it's actually quite natural. And the structure to keep in mind here is that tan alpha plus beta gives you a fraction where in the numerator you have a sum, and in the denominator you have 1 minus the product of tan alpha and tan beta. And then tan alpha minus beta, then you get the same kind of structure. So for the numerator, you have the difference, tan alpha minus tan beta. And in the denominator, you have 1 plus the product. So it's in each case the opposite sign. So you have to be a bit careful. So if you have a plus here, then you get a minus here. And if you have a minus here, you get a plus here, and a plus here, and once more, we will not cover the proof, but you could, with not too much work, do this yourself. If you wanted to know how this works, you could start with tan alpha plus beta is sine alpha plus beta divided by cosine alpha plus beta. And then you work out with the addition formulas what each term is. So this becomes sine alpha cosine beta plus cosine alpha sine beta, cosine alpha cosine beta minus sine alpha sine beta. And you start seeing that structure already a little bit. So here you have that plus sign that we want on the right hand side, and here you have that minus sign. The only thing is we want a 1 here on the right hand side. So what can we do? Well, we can divide both sides by cosine alpha cosine beta. Okay, let me do that just real quick. Sine alpha cosine beta plus cosine alpha sine beta, cosine alpha cosine beta, then fraction, cosine alpha cosine beta minus sine alpha sine beta, and divided by cosine alpha cosine beta. And now we're almost there. Now you just divide each fraction up into 2 and you simplify. And with a little bit of algebra, what will come out is precisely what we have on the right-hand side, the tan alpha plus tan beta 1 minus tan alpha times tan beta. So here, I normally don't like skipping steps, but I just wanted to give you a proof to show that this is not a magical formula that comes out of nowhere. With a little bit of calculation, you can derive it. Moving on, then we have the double angle formulas. And they're again given here on the right of the slide. Here, these are super useful formulas, especially you'll see when we have trigonometry and when we do things with integration of trigonometric formulas. These will come back quite a lot. So what do these formulas do before we try to derive them? Well, they tell you something about a trigonometric expression that involves 2 times theta, and they allow you to simplify that to an expression involving just theta. So on the right-hand side here, you see 2 theta, 2 theta, 2 theta. Sorry, that's on the left-hand side. And then on the right-hand side, you have theta, 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 theta. So where do these formulas come from? Let's take the first one. So sine 2 theta, I can write that as sine theta plus theta. That's what 2 theta is. And now I just use my addition formula. Sine theta, cosine theta plus cosine theta, sine theta. And now I see I have 2 times the same thing, sine theta, cosine theta. So that gives me 2 times sine theta, cosine theta. So here I used the addition formula. That gives me the first formula here. And then let's also derive the second one for cosine. Cosine 2 theta. The same game. We write 2 theta as theta plus theta. And we use the addition formula cosine theta minus sine theta sine theta, and that gives me cosine times cosine, that's cosine squared theta minus sine squared theta. So that gives me the second formula, but there's 2 slightly different formulations of the same expression that I also want to share with you. So I'll call this first one 2 prime. So here if we start with cosine 2 theta, and we write it as cosine squared minus sine squared theta. Then what I can do now is I can use my fundamental identity and I can write cosine squared as 1 minus sine squared theta. And why is that? Well, remember the fundamental identity says that cosine squared plus sine squared is always equal to 1. So I use this formula when I've just written down to replace cosine squared by 1 minus sine squared. And so that then gives me that cosine 2 theta is also equal to 1 minus 2 times sine squared theta. And I can also do the opposite. I can focus on the sine squared. So here, let me write the formula again. Cosine to theta is cosine squared minus sine squared. And now I write sine squared as 1 minus cosine squared theta. And what that gives me is, now I have a cosine squared plus another cosine squared, so 2 cosine squared theta minus 1. So I get 2 more formulas to add here to my formularium. Cosine to theta is 2 times cosine squared minus 1. That's also equal to 1 minus 2 times sine squared theta. So with that, let's maybe make a quick example. So for the example, let's prove that the following statement holds true. 1 plus tan x divided by 1 minus tan x is equal to tan pi over 4 plus x. So this looks a bit like a shift formula if we squint at it, but instead of adding pi over 2 or pi, we add pi over 4. And what you'll also notice is that a lot of the exercises, maybe not this week, but definitely next week, are going to be of the form, prove this, prove that, and so on. So it's good if you already know the basic trigonometry, focus a bit on the proofs. So how can we prove this statement? Or if you've never proven anything, how do you prove something? How do you go about proving something? Well, keep in mind that a proof is like trying to convince someone of the fact that you're right. Like you have an idea and you want to tell someone about it, and you want to convince them, so that and in convincing them, you try to explain every step in detail in such a way that they cannot argue with each of the individual steps. So what do we do here, or what can we do for a proof is, well, we can start from the right-hand side, the tan pi over 4 plus x. And we can say, well, I can use my addition formula on this expression and write this as tan pi over 4 plus tan x divided by 1 minus tan pi over 4 times tan x. So that's by the addition formula for tan. And now this is already starting to look quite good. So now I have that tan pi over 4 in there. So if you don't remember what that is, you can write out what it boils down to. It's sine pi over 4 divided by cosine pi over 4. And those are both equal to square root of 2 over 2. So then square root of 2 over 2 divided by square root of 2 over 2 is 1. So the tan of pi over 4 is just 1. So here I have that this is equal to 1 and this is equal to 1. And so if I substitute that, I get that 1 plus tan x in my numerator and 1 minus tan x in my denominator. So very simple proof, only 2 steps, addition formula and then calculating what that constant value is. but nevertheless, a small little thing. So with that, let's move on in our quest to explore the trigonometric formulas. We also have half-angle formulas, and they allow you to do what you think they do. They go the opposite way from the double angle formulas. So they take something that's written in theta and rewrite it as something in 2 theta. So here, in each case, we have theta, theta, theta on the left-hand side, and we have 2 theta, 2 theta, 2 theta on the right-hand side. And why are these useful? Well, for instance, when we do integration of trigonometric functions, it's going to be much easier to integrate a cosine, even if it's cosine 2 theta, than it is to integrate cosine squared. So in some cases, rewriting a square as cosine 2 theta or sine squared as minus cosine 2 theta is the right thing to do. We're not going to derive all of these formulas. Let's maybe just do one. So how do we prove these formulas? Well, let's start from the double angle formula. Where we had cosine 2 theta is equal to, for instance, 2 times cosine theta minus 1. Cosine squared. Yeah. And now, if I bring the cosine squared to the left-hand side and I divide everything by 2, what I get is from that cosine squared theta is equal to cosine 2 theta plus 1 divided by 2. So that's precisely the first formula that I have on the blackboard here. And then I can also start from the other double angle formula, the one that said that cosine 2 theta is 1 minus 2 sine squared theta. And if I rearrange the terms here to free up sine squared theta, then I have that sine squared is 1 minus cosine 2 theta divided by 2. So that's the second formula that I have here. And then the last, the one for tan, how does that follow? Well, you just divide sine squared by cosine squared, and you will get what the right-hand side gives here. As a quick example, and I'll just sketch a few steps, we'll start with the expression cosine squared x sine squared x, and what we'll do is we'll write this expression as something in cosine sine, so without any powers. So this is what we start from, cosine squared sine squared, and we want something that doesn't have any power. So no more square and no more square here. So what can I do? Well, I can first use my half angle formula to write this as 1 plus cosine 2x divided by 2 times 1 minus cosine 2x divided by 2. And I can factor out the 1/2 from the denominator here and here to give me 1/4. And then I have 1 plus cosine 2x times 1 minus cosine 2x. So here I'm going to use that formula that says a plus b, a minus b is a squared minus b squared. And I'm going to write this as 1 minus cosine squared of 2x. And so now, am I done? Well, it's already looking a bit easier, but I'm not done because I still have a cosine squared here and a question asks no powers, just sine and cosine. So what I can do now is I can use my half angle formula one more time on this. So if I write this with the half angle formula, then what I have is that this is equal to 1 plus cosine. And now cosine of what? Well, with the half angle formula, you always take the thing that's in the cosine squared and you double it. So in this case, we get cosine 4x divided by 2. And now let's clean that up a little bit. So I get 1/4 times 1/2, that's 1/8, minus, and then the, that's right. The upshot is, so I get 1/4, and then the cosine here is also divided by 2, so get another 1/8 times cosine 4x. Or in other words, maybe a bit cleaner to write this as 1 minus cosine 4x divided by 8. And now we're done because we have something that involves only cosine and sine. There are no more powers. And then the last set of formulas, and it's unfortunately another massive set, are the so-called product to sum formulas. And here what I'm doing is I'm doing the what the name indicates. I take a product of sine and cosine. So sine cosine, or cosine sine, or cosine cosine, or sine sine, and I express it as a sum or a difference of sines and cosines. And again, we can stare a bit at the structure. Sine alpha cosine beta gives me sine alpha, so sine plus sine. And what do you have in as the argument? Well, in each case, you have something alpha plus beta and something alpha minus beta. So for the product of sine and cosine, you get sine alpha plus beta plus sine alpha minus beta. And then if you switch cosine alpha, cosine beta, you get sine alpha minus, sine alpha plus beta minus sine alpha minus beta. And then for cosine cosine, you get two cosines, cosine alpha plus beta plus cosine alpha minus beta. And then be very careful here, sine alpha, sine beta. We always think, oh, sine, that's the nice one, the one that doesn't pick up an extra minus sign. But here the structure is sine alpha, sine beta is cosine alpha minus beta minus cosine alpha plus beta. So be vigilant and don't forget this minus sign. So here too, I will not give you the proofs. They're quite a bit of work to derive, but they are also quite useful. And then the last set of formulas is the sum to product formula. So they go the other way around. They go from a sum of sine and cosine, or a difference, and they give you a product of terms. So here now so maybe go back to the previous slide. So here I had a product and I went to a sum or a difference. And here what I have is a sum or a difference, and I turn that into a product. These formulas, the sum to product formulas, they follow from the product to sum formulas, but I will not go into details. And then before we move on to the next part, a little bit about the fundamental period of trigonometric functions. And for that, I'm going to refer to this slide right here, the one that you see with all the graphs. So we have three graphs. The first is the graph of sine x. Second one is a graph of cosine. And the last is a graph of the tan function. And these are graphs that you should be able to recognize on site, and you should have a good visual understanding of what the sine and the cosine look like. So let's point out some salient features. Well, first of all, I know that if I have sine of an angle, x, and I add 2 pi to that, then what I get is the same thing as if I just take the sine of x. So remember, I can always add or subtract 2 pi, 4 pi to an angle, and that doesn't change the sign. And I see that also in the graph because, for instance, sine 0 is 0, sine 2 pi is equal to 0. And what I get is that the sine function does this one oscillation between 0 and 2 pi. But then once I go beyond 2 pi, then basically the function does exactly the same thing again. So in particular, for example, if I choose another color here. So for instance, if I take this value right here, this is halfway between 2 pi and 3 pi. So that is 5 pi over 2. So this value right here is going to be the exact same as this value right here for pi over 2, and both values are equal to plus 1. And why is that? Well, 5 pi over 2, that is pi over 2 plus 2 pi. And so you see every 2 pi, the function just repeats itself. And that's what we mean when we say that the fundamental period of the sine function is 2 pi. So let me add that here on top. So this is, length is 2 pi. The fundamental period is 2 pi. The function repeats itself every 2 pi. And why is it called the fundamental period? It's the smallest such value. So you can say, well, sine x repeats itself every 2 pi, but it also repeats itself every 4 pi. So 4 pi is a period, but it's not a fundamental period because a fundamental period is the smallest period. So, and then why is there no period smaller than 2 pi, you might ask? Well, if you look at the graph, you see between 0 and 2 pi, it doesn't repeat itself. It does completely novel things. So 2 pi really is the smallest period. And now if you look at the graph of cosine, you see the same kind of thing. So between 0 and 2 pi, which is here, the function starts at 1 and then crosses 0 at pi over 2, goes to -1, crosses back at 3 pi over 2, and then goes back to +1 here. And then afterwards, what happens is the function just repeats itself. So this is also a consequence of the fact that cosine x plus 2 pi is just cosine of x. You can always add or subtract multiples of 2 pi and you don't change the cosine. So here again, we say that the fundamental period is 2 pi. Oh, sorry. Every time my sleeve touches the screen, it tries to skip a slide. So let me try not to do it. Okay. And then the last graph, and this is one that's worth staring at for a bit. So this is the graph of tan of x, tangent function. And here what we see is two interesting phenomena. So first of all, it also repeats itself. You sort of see these copies of the blue graph here. but they don't repeat with period 2 pi, they repeat with period pi. So the function does something unique between minus pi over 2 and pi over 2. So here the fundamental period is pi. It does something unique between minus pi over 2 and pi over 2. And then beyond pi over 2, the behavior of the function is just a copy of what it already was. And same thing if we subtract pi over 2 pi, then we get another branch of the function, but it has exactly the same shape as the one between minus and plus pi over 2. And this follows also from something that we've already seen. We know that if we take the tangent of x plus pi, that is equal to the tangent of just x for all x. That was one of the shift formulas that we see. Just double check my notes. And then one last thing that I want to highlight, and I'll do it just here on the bottom of the slide. So what if you have another function? So what if we have to find the fundamental period of, let's say, sine 2 times x? What you can do is, well, you can try to graph the function and that would work, or you can try to think a little bit about what is it that we mean by the fundamental period. So we know that the fundamental period should be something where you, if you take the function, so if you take the function, so sine 2x, and you add 2 pi to it, then what we get back is that 2 pi doesn't matter, that doesn't change the function value, so we get back sine 2x. And now we can write the term in between the argument here as sine 2 times x plus pi is equal to sine 2x. That's the same expression, just rewritten. So what this tells us in human language is we can add pi to x, and that doesn't change sine 2x. So from that, we have that the fundamental period is equal to pi. And in fact, if you graph that function, and I'll graph it really slowly, really small here, you basically get a sign that goes twice as fast as a normal sign. So if this is sine 2x, then this, let me make sure I have it right, and this is sine. So twice as fast as the normal sign. Sorry, it's a bit crammed here, but the calculation is probably more useful at this point. With that, we're done with the standard formulas for trigonometry. If there are any questions, I'm happy to take them now or at the end of the class, or let's maybe keep them for the end of the class because I want to catch up a bit on time. And with that, I also have a little bit of material to start introducing to you now. So I will save my presentation for future reference. And share my screen again for the second part of today. So this is trigonometry 3. Can you see my full screen? The presentation on the full screen, not PowerPoint with all the buttons and everything. If you can, give me a quick shout out. Otherwise, yeah. Looks like we're good. Okay, thank you. Okay, put this somewhere. Okay, so now what we will do is we will relate the trigonometric functions that we've seen to things that have to do with triangles. And this is not a, like, why would we do that? Well, first of all, trigonometry was invented to say something about triangles. And when I say triangles, I want you to think about practical problems that involve triangles. We're not interested in triangles for the sake of triangles. We're interested in them because a lot of things involve triangles. So one of the problems, for instance, that we'll see is that change my color, yeah. One of the problems, for instance, that we will look at is you are here and you look up at some tower somewhere in the distance. Let's say it's a lighthouse tower. And you know you are a certain distance away from the tower. Let's say you are 2 kilometers away from the tower, and you see the tower under an angle of 10 degrees. And you want to know, okay, how high is the tower? What is the height? That's the typical archetypical problem that we will solve. We will also do a bit more involved problems, and I have a fun problem given all of the zombie movies that you've seen on Netflix and on other streaming providers. If you have a zombie running towards you at a certain speed and you observe him or her, or I don't know if a zombie has a gender, but you want to escape from the zombie, and you want to calculate its speed, what does trigonometry tell you about that? So that's one of the problems that we will cover the next lecture that we see each other, but that's just to set the stage. Also, in the word trigonometry is already the fact that we're going to deal with triangles. Tri in trigonometry means 3, and gonos or gonometry, this comes from the Greek word for angle. So trigonometry means measuring things that have to do with 3 angles, so triangles. Okay, I already covered this. What are we going to do this time? Well, we'll look at trigonometry in right-angled triangles and in general triangles. So right-angled triangles are triangles that have a right angle. General triangles do not necessarily have a right angle. We'll look at both cases separately. And then the other topics were normally for Wednesday's lecture, but I will ask you to look at a video instead. So let's start with right-angled triangles. And I'm going to start by drawing such a triangle, like so. And I'll call the vertices O, P, and Q. So I have a right angle here. And what I'm going to do now is I'm going to put myself here in the origin O. And okay, let's also call this angle here theta. And I'm going to draw a unit circle centered on the vertex O. let me find a nice color. So let's say the unit circle looks something like this, like so, and then it continues like here, but I'm not going to need those points. So this is a unit circle with center O. And now I'm going to take the point that I obtain here and call that P. And I'm also going to draw a perpendicular here, so a line that's at right angles to the base, and call that point Q. And so why do I do all of these things? Well, what I want to do ultimately is relate the length of the sides, OP, OQ, and PQ, with some trigonometric expression involving theta. So now that we have this smaller triangle, let's say something about sine and cosine of theta. So first of all, before I forget, let's not forget that this length, OP prime, sorry, that is equal to 1, because it's a unit circle. So P prime is at distance 1 from the origin, and that's going to be important. So now that we have that, what do we know about sine and cosine of theta? So let's start by sine theta. So for sine theta, well, what do I know? I know that sine theta is the y coordinate of P prime. So sine theta is precisely the length of the PQ segment that I've indicated on the figure. So P prime, Q prime, the length of that is equal to sine theta. And then also, let me maybe put that a bit in a color so that we can distinguish it. So this length right here that I'm shading in green is this length P prime, Q prime. And then cosine theta, well, what is cosine theta? Cosine theta is the x coordinate of the point P prime. So it's the length of this segment right here that I shade in red. So the length of OQ prime in red. And now, what does that tell me about my bigger triangle? Well, in order to understand that, I need to look back at the relation between the bigger and the smaller triangle. And so what I have here, if I compare these two triangles, is I have two triangles, triangle OPQ and triangle OP prime Q prime. And these two triangles are similar. And what does that mean? Similar triangles are triangles that have the same angles, but that just differ because one is a blown up version of the other, or one is a shrunk version of the other. That's what similar triangles mean. And here you can see very well that these two triangles, the small one and the big one, are similar because they share an angle here, that theta, and they both have a right angle. So all three of their angles are the same, and hence they are similar. And what does similarity give us? Well, it doesn't tell us that the lengths of the sides are equal. You can see that from the figure that they're not, but the ratios of the lengths are equal. So in particular, we can write that OP prime divided by OP, those lengths are equal to OQ prime divided by OQ, and that's equal to P prime Q prime length divided by PQ. So the ratios of each of the corresponding sides are equal. P prime Q prime divided by PQ, OP prime divided by OP, and so on. And there's one more thing that we know. And what do we know? Yeah, and we also know that OP prime is still equal to 1. Okay, So now let's put all of this that we've learned together, and let's go back to our sine. So we already have that sine is p prime q prime, the length of that. And now if I go look at my expression star here, I can also write that as OP prime times PQ prime divided by the length of OP. And now I use the fact that OP prime is equal to 1. So this is equal to 1. And therefore I get that sine theta is PQ divided by OP. And now if I stop calculating for a second and I look at the triangle, what that tells me, it tells me, and I'm going to shade over the things, or let me maybe see, I'll just take the laser pointer. I don't want to mess up my figure. So what I have is, I'm saying something about sine of theta, and I have obtained an expression that says sine theta is equal to the length PQ, so the opposite side of the triangle, divided by OP. This is the hypotenuse, the longest side in the triangle. So once again, sine theta is opposite side divided by hypotenuse. So I can write it systematically as opposite side divided by hypotenuse. Now I can do the same thing for cosine. I get that cosine using my formula star is equal to OQ prime. So that's OP prime again times OQ divided by OP. Now once again, OP prime is 1. So I get OQ, the length of OQ divided by OP. And once again, looking at the big triangle, cosine theta is the length of OQ, the base of the triangle, divided by, again, OP, the hypotenuse. So we get the adjacent side divided by hypotenuse. And last, we can also add the tangent. So the tangent is sine theta over cosine theta. And we can use these formulas that we've already obtained now to write this as the opposite divided by the adjacent. And let me just, for the sake of posteriority, write down what all the sides are. So this here is the opposite side. This side is the adjacent, and this, the longest one, that's the hypotenuse. So with that in mind, let's exercise that for just a second, and let's look at an example. So I'm going to draw a triangle, and we have a few things given of that triangle. We know that this angle is alpha, this side is 3, this is x, and this is 4. And we want to find sine alpha, cosine alpha, and tan alpha. Then the first thing that we will do is, well, we'll try to find that x. So by Pythagoras' theorem, we have that 3 squared plus x squared is equal to 4 squared. And if I rearrange that a bit, I get x squared is 16 minus 9, which is 7, and therefore x is square root of 7. And now I can use my trigonometry to say, well, sine alpha is the opposite divided by the hypotenuse. So that's square root of 7 divided by 4. Cosine of alpha, that's the adjacent over the hypotenuse. So that's 3 over 4. And tan alpha is the opposite over the adjacent. So that is square root of 7 divided by 3. Another example that we can do quickly is the following. So I take another right angle triangle with now an angle 30. Call this A and B, and the hypotenuse is 12. And I want to find A and B. So how can I do that? Well, I can start with what I know. So I can take the sine of 30 degrees. And I know the sine is the opposite divided by the hypotenuse. So that's A divided by 12. And I also know that the sine of 30, that is 1/2. So this is one of the values that comes back a lot. Sine 30, that's sine pi over 6. That's 1/2. And conversely, I have cosine 30. That's the adjacent over the hypotenuse. So that's B over 12. And cosine 30, that's square root of 3 divided by 2. And now from the first expression, I will get that A is equal to 12 divided by 2, so 6. And from the second expression, I get B is square root of 3 divided by 2 times 12. So that is 6 times square root of 3. And you can check actually with Pythagoras' theorem that if you square these two lengths and you add them together, that you get 12 squared back. Then the last problem is sort of a wordy problem. I will leave that to you to figure out. So here I will let you do this. So basically what we have is we are sitting in the park, somewhere in Songdo. We're sitting on top of the hill here, and we look at the POSCO tower in the next block. And we see the POSCO tower under an angle of 30 degrees. So if I make a drawing, I'm here in the park. I have the POSCO tower right here. I'm looking up at the top of the tower. Maybe I see my friends having a cocktail at the top of the tower. And I observe them under an angle of 30 degrees. And knowing that the tower is 300 meters tall, how far am I from the base of the tower? So what is the length here of the base of the triangle? So I'll let you figure it out, and you should find that x is square root of 3 times 300, or about 520 meters. And actually, yeah, it works out. Even if you look on Google Maps, it's about 520 meters. With that, I will stop here because we're almost at time. Let me see, we have a couple more minutes in case there are any questions. Just check the chat. Okay, I don't see any questions. Let me maybe just briefly say what we will, or what we would have covered next. I will go through this quite quickly just to point out the formulas. So the thing that we didn't get to today, question. So yeah, there's a question about, can we use a formula sheet in our test? Yes, so you will be able to use a formula sheet for the test. So the next few topics have to do with general triangles. And here we have two sets of formulas that we will cover. But I will go into that next time. And another question, do we have a practical session tomorrow? Yes, we do have a practical session tomorrow. That's a very good question. So let me go back here. So yes, there is a practical session tomorrow already. I think, but do double check that it is in room GH203 from 1:30 to 4:45. And on Thursday, there's the other session, which I think will be in room 104. But do check the schedule. And then yeah, there's a question about uploading the slides to Eufora. I will do that at the end of today. With that, we're at the end of the lecture. I just want to remind you, if you haven't already, to double check your group assignment on Eufora. It should be the case that you have no scheduling conflicts. If you don't see your group assignment on Eufora, or if you see that you have a scheduling conflict, then contact me as soon as possible. Other than that, I thank you for your attention, and I will see you again in precisely 1 week from now for the next lecture. Thank you very much, and have a good rest of your day. Bye.